Let's say we're told to find the average rate of change between 2 points. So let's say between x equals 1 and x equals 6, we have to find the average rate of change along the function y equals 2x squared minus 3. So let's graph what we have here. So y equals 2x squared minus 3. If you recall how to graph quadratics, it's going to look something like this, where this here is negative 3. And to figure out the average rate of change between 1 and 6, we have to say, okay, well, here's 1. 6 is up here probably like this. So you have these 2 points. And what does it mean when they ask for the average rate of change? Well, that means they want the slope of a straight line that goes between those 2 points, right? So if you find the slope, which is m, of that line, that's equal to the average rate of change, right? We have to say average because the rate of change along this line is changing all the time, right? Like over here, it's kind of not that steep. It's kind of flat, but then over here, it's very steep if you imagine the slope over here. And so the slope is changing, right, at every point. So we have to find the average rate of change. That just means a straight line between those 2 points. And how do we do that? Well, I have to know what the y values are at those 2 points, and then we can do rise over run, right? So I'm going to plug in 1 for x to figure out the y value. So y equals 2 times 1 squared minus 3. That's equal to negative 1. So one point we have right here is 1, negative 1. That's this point. And then to find the other point, I got to plug in 6. So y equals 2 times 6 squared minus 3. That's going to equal 36 times 2 is 72, minus 3 is 69. So that point up here is going to be 669. Okay? To find the slope between them, we're just doing the rise over run, right? So m is equal to y2 minus y1, so 69 minus negative 1, divided by x2 minus x1, 6 minus 1, and you end up getting 70 over 5, which is the same thing as 14. So 14 is the average rate of change between these 2 points. Okay, let's do another example. Let's say you're given a graph, right, and they actually draw it out for you. They tell you it looks something like this. Let's say you have a point over here. This is point B. And point B is at, we'll say 6, 8, right? So 6, 8 is that point B. And then you have a point A down here. And point A, we'll say, is at negative 2, negative 1. Okay? That's point A. And let's say you want to find the average rate of change from point A to point B. So a line from A to B looks like this, right? So the average rate of change between those 2 points, it's the same idea as the previous question, right? To find the average rate of change between A and B, you find the slope of AB, which is just the rise over run. So you could say, your y2 minus y1 over x2 minus x1, same as the last one. I just didn't write it out last time like this, but it's the same thing. So your y2 is 8 minus your y1 is negative 1 divided by x2 is 6 minus negative 2. So you get 9 over 8. So 9 over 8 is your average rate of change. So you go up 9 over 8, right? That's the slope. Now, that's average rate of change. Hopefully that made sense to you. And with that in mind, we're going to look at something new. This new thing is called instantaneous rate of change. Instantaneous rate of change. Now, what does this mean? Well, if you imagine a curve, you draw it like this. Okay, that's our curve. If you imagine a point right here, and you're on this point of the hill, right? Or I guess it's a valley in this case, and you're walking, it's not too hard to walk from there to here, right? It's not that steep, right? If you're going from there to there. But if you're walking from here to here, well, that's a pretty steep climb, right? And so the point here to illustrate is that the slope of this curve is different everywhere. It's constantly changing, right? I mean, the slope at this point is different than the slope at this point, right? It's changing very slowly from each point to the next. And so the idea is, can we find or estimate what the instantaneous rate of change is at any given point? I mean, we know what the average rate of change is between 2 points, And that gap between those 2 points can get smaller and smaller, right? You can find the average rate of change between these 2 points, but can you find the instantaneous rate of change? So the rate of change at just 1 point like that. Well, that's what we're going to do, or at least we're going to try to estimate it. And for the curve we're working with, I'm going to draw slightly differently. It's going to look like this, okay? And this down here is at -1. And then we have a point up here, and that point is going to be at 3, 8, okay? Now to find the slope of this, you can actually represent it graphically using what we call a tangent line. And a tangent line is just a line that touches the curve at 1 point, okay? And the slope of this tangent line is equal to the instantaneous slope at that point. So if you were to find the slope of this line, right, you do your rise over run here, you're going to get the same slope as you would get if you were able to take the instantaneous slope at that point, okay? So how do we do this? Well, one method you could do is use the original function for this line, and I'll write that out. The original equation for this line is f of x equals x squared minus 1. Okay, this is the graph of this curve, all right? Hopefully you can see that. Now, 3, 8 is a point on the line. We know that, right? Because if you plug in 3 for x, 3 squared is 9, minus 1 is 8. So that is, in fact, a point on the line. What we can say is that if you have the point 3, 8, you can find another point that's very, very, very close to it. So close, in fact, that if you find the average rate of change between the two, you're getting a very good estimation for the instantaneous rate of change at this point, right? So I'm going to use a point like 3.01 as an example. So f at 3.01, and that's going to equal 3.01 squared minus 1. We can calculate that. You're going to get 8.0601. So a point just to the right of this one, right here, is just a little bit higher as well, right? And it's so incredibly close, you can't even really draw it graphically unless you zoom in a lot, right? Like 8.06 is just a hair above 8, right? And so that's the next point that we're going to use. So now we can find the slope between 3, 8 and the point 3.01, 8.0601. Again, this is just going to give you a pretty good estimation for the instantaneous rate of change. So let's do this. So the slope is going to equal the change in y. So 8.0601 minus 8 divided by the change in x. So 3.01 minus 3. And the answer you get here is 6.01. And because this is estimation, it's likely that your answer here is actually just 6, right? And that the slope at that point is just equal to 6, okay? And what's interesting is right now you have to do your best to just estimate what these answers are. But once you start taking calculus classes and you're able to derive functions, that's a technique to find these answers exactly. And I can tell you that 6 is the correct answer if you were to take the derivative of this. Now, we're not covering that in this video. That'll be covered next year when you guys take calculus and vectors, if you choose to take it. But that's really what that's all about, right? It's about finding the rates of change of a function or the slopes of a function. Now let's move on to another example here. Let's say the following function represents the speed of a car in kilometers per hour in terms of time, t, which is also in hours, over the course of a trip. So you have this function v at t, and v at t equals negative 240 times t minus a half squared plus 60. And again, this represents the speed of a car. So this is the speed that you're driving, and it's in kilometers per hour. And it's in terms of t time, where t is your time in hours. And your trip is 1 hour long, so t is actually going to go between 0 and 1. So when it's at 0, that's the start of your trip, and when it's at 1, that's the end of your trip. Okay? So this function basically tells you how fast are you going at any given point in the trip. If you want to figure out how fast you were going, exactly halfway through the trip, you plug in 0.5 for t, and it'll give you the speed you were going at that time. Now, if you want to graph this, it's a quadratic equation, right? And it's in vertex form. So you could say that your vertex is at the point 1/2 60. So 1/2 60, like that. And you have roots at, well, where are the roots going to be? Well, I think the roots are going to be at 0 and 1. because this is your t-axis. If you plug in 0 here, you're going to get negative a half squared, which is a quarter. A quarter times 240 is negative 60. Negative 60 plus 60 is 0, right? So 0 is going to be one of your roots. You plug in 1, the exact same thing happens. 1 minus a half is a half, squared is a quarter, right? Times this, it's going to go away. So 1 and 0 are your roots. So it's going to look like this, right? So you get faster and faster as the trip goes on, and then the second half of the trip, you're going to get slower and slower and slower until you come to a stop, right? Because this represents your speed, okay? Now, the question here is, what is the acceleration of the car at 45 minutes? Okay, so what's the acceleration of the car at 45 minutes? Well, I could tell you the speed of the car at 45 minutes, right? 45 is 3/4 of the hour, right? So it would be 3/4 of the way through this. So because that time's in hours, you just say 45 minutes is equal to 0.75 hours. So you plug in 0.75 for t, and then whatever you get as an answer, that's your speed that you're traveling at that time. They're not asking for speed, they're asking for acceleration. Well, what is acceleration? We have to define that, right? Acceleration is how quickly your speed is changing. Okay, think about that. So when you're driving a car and your car speeds up, it's accelerating. When it slows down, you might say it's decelerating, but that's a type of acceleration, right? You're just slowing down. So acceleration is the rate at which your speed is changing in terms of time. And actually, the units for acceleration in this case are going to be kilometers per hour squared. Okay? Because your speed, which is kilometers per hour, is changing in terms of time, which is also h. So you have kilometers per hour, which is kilometers per hour squared. That's the units for acceleration, okay? And if you take a physics class, you'll be very familiar with this concept. So we have to find the acceleration at that point. And it's going to be negative, right? Because you're slowing down at that point. It's in the second half of the trip. So what we can do is estimate this using a point that's very, very close to that, right? So first we got to figure out what's the first point, right? Well, you plug in your 0.75. So v at 0.75 to find the y value, or in this case the v value at that point. So you're going to have negative 240 times 0.75 minus 0.5 squared plus 60. Calculate that, and you're going to get 45, and that's going to be kilometers per hour, right? Just a coincidence that it's the same as the 45 minutes, right? That has nothing to do with this. So the first point we have is 0.75. So at 0.75 hours, you're traveling 45 kilometers an hour. That's what that means, okay? Now that's the first point. What you want to do next is use a point that's very, very close to that. Like say v at 0.7501 instead of 0.75. Calculate this now. So I'm just going to plug it in. Write it all out again like that, but I'm using my 0.7501. And when you calculate this, you're going to get 44.9879976. I'm keeping a lot of decimals just to be accurate, but if you're using your calculator, you can save those. You can save that answer and use that in your calculation, right? So this second point that we have is 0.7501. 44.9879976 approximately. So you've increased your time just barely, so just a little bit later, and your speed has just barely decreased, but it is decreasing, right? And because this point's very close to it, when we find the slope between these two, that'll be a good estimation for the instantaneous rate of change, or the acceleration at that exact moment, okay? So let's go ahead and find the slope between these 2 points, right, or the rate of change between these 2 points. So you'll have the rate of change is equal to, you're going to do 44.9879976 minus 45, right, because this one is further to the right, and you should get a negative answer because we're slowing down, divided by 0.7501 minus 0.75. And if you calculate this, on the top, this is your change in kilometers per hour. The bottom is your change in hours, right, because the top is your speed, the bottom is your time. Right, your y and your x, your v and your t. So what you get is negative 120.025 kilometers per hour squared, right? It's negative because that implies that you're slowing down, right? So you're slowing down at a rate of 120 kilometers per hour squared, which means that every hour that passes, your speed's going to decrease by 120 kilometers per hour. Think of it that way, all right? So that's your acceleration, all right? And that's going to be actually your final answer. Okay, hopefully that makes sense.